This is part 3 of chapter 11, The Dynamic Planet. We have covered in parts 1 and parts 2, talking about endogenic processes, um, and the different layers of the Earth, what those layers are made of. And here, starting in part 3, I want to talk about the geologic cycle. We could also think of this as a system that includes all physical processes that occur in and on Earth. And that's a huge, huge, huge system. However, that system is important to understand some of the inputs and some of the outputs. The main uh, two things that fuel the geologic system, they are endogenic processes, where the energy is coming from inside the earth, right? We already talked about endogenic, endo meaning inside, but also exogenic processes, which are external, focusing on the outside of the earth, the energy coming from outside the earth, the energy coming from the sun, mainly. The solar radiation affects the outside of the earth. The energy is outside the earth also, uh, i.e., the sun. But exoskeleton, right? Those are skeletons that are outside the body of some organism. So exogenic, outside, um, and so things that fuel the geologic cycle. It's energy that comes from inside the earth, energy that comes from outside the earth. These processes are balanced. Not the amount of energy per se is balanced, but the rate at which they work. Um, the endogenic processes, things that are made through plate tectonics, volcanoes and earthquakes and faults. Um, those are all processes that are building the crust up. So again, the mountains are made through plate tectonics, but those mountains are increasing the height, the thickness of the crust. Whereas exogenic processes tear the landforms back down. They create interesting uh, landscapes in the process. But things like the sun and rain and wind, that all works to erode the processes back down, which is a good thing that they're balanced because as you build something up, it comes back down. That leaves the earth relatively balanced. We're not building out and out and out and out further and further, unchecked. Neither are the exogenic processes eroding everything down, um, to, uh, to deeper and deeper levels. We're not doing that either. They are balanced. So, we have a depiction here of the geologic cycle. It's sort of starting over here with our exogenic inputs, mostly the sun. And on the other side, we have the inputs being the endogenic energy from that radioactive decay in the center of the Earth. So on either side of the whole geologic cycle here, um, the inputs for the exogenic system mainly affects the atmosphere and water slash weather systems. And we're actually going to talk about exogenic processes specifically for most of the rest of the semester. These chapter numbers are incorrect, but they're the chapters on our syllabus. Whereas the outputs here for our endogenic processes, which is mainly what's fueling plate tectonics, we're only spending 2 chapters on that. This chapter 11 and chapter 12. Again, those numbers are incorrect. Um, okay, so both of these things, internal and external processes, we have three main subsystems to consider. The hydrologic cycle, or the water cycle, you might have heard of, the rock cycle, which you also may have heard of, and the tectonic cycle, which maybe you may or may not have heard of that. But the fact is that all three of these subsystems is what makes up the whole geologic cycle: rocks, water, and tectonics, building the earth up and tearing it back down. I just wanted to take a brief look at the first, um, well, this will be the first cycle, the rock cycle. We're not going to spend a lot of time talking about the different aspects of the rock cycle, but um, it's just important to know because, again, this is what our landforms are made of, or how they started, and affect what the landform might look like, um, how it how fast it might form or how fast it might change. That's all dependent on the rock or the sediment properties. So the rock cycle itself is a circle, also why it's called a cycle. And we could start anywhere in this cycle to kind of talk about the interrelatedness of the different types of rock. We have the igneous rock, sedimentary rock, and metamorphic rock. Those are the three types of rocks on the planet. I'm going to start right here. Melting. Melting forms magma inside the earth. Magma doesn't exist everywhere in the mantle, just in certain places. But in any case, we start with a magma and it cools, or it gets erupted and cools outside the earth. That is what creates the igneous rock. Once, in this case, we're looking at lava. Once that lava cools, it forms a rock. That igneous rock could then be exposed to the elements. As I said, weathering occurs due to wind, rain, ice, which maybe we don't want to talk about. Sorry. Or water. Is that one? Uh, in any case, we get the solid rock broken down into pieces. And those pieces then they can be compacted, cemented, formed into a rock. Rock made up of sediments. We call it a sedimentary rock. The sedimentary rock then could be buried, heated, exposed to higher and higher pressures. This is called metamorphism. And that would create a metamorphic rock. The heat or the pressure can only be so high uh, before you melt it. You don't want to melt a rock if you want to form a metamorphic rock. What happens if you melt the rock instead? The temperature is too high and the rock melts instead. What happens? It becomes a boop, igneous rock. Yeah, if you melt any rock, right? Metamorphic too, it becomes an igneous rock. So metamorphic rocks form at temperatures lower than the melting point. But again, yeah, we could start here and melt the rock and go through the whole cycle all over again. These blue arrows inside the circle indicate that you can go from one point to any point on this circle. So, say we've have some great big layers of sedimentary rock. Well, this sedimentary rock can be eroded instead of buried and metamorphosed. It could be re-eroded and break down into little tiny parts, and it can make a sedimentary rock again. And in fact, we have a lot of rocks at the surface in the crust that do or have gone over and over that little path. But this, in the same way, we could take a sedimentary rock and just straight melt it, skip the metamorphism. Temperatures shoot right up into melting, and then we can directly make an igneous rock once that melt cools down and solidifies. Um, Again, one other example. Well, igneous rocks can be metamorphosed. So if we take these lavas or the magmas that cool, we can heat them up a little bit, but not melt them again. So then they become metamorphic. Or we can take an igneous rock once it's crystallized and cooled. We could remelt it, just straight on remelt it and cool it and make maybe a different igneous rock. So that's the purpose of this diagram. It shows the all the different aspects of the rock cycle. Um, I just have one slide about igneous rocks because we don't need to know a whole lot um, about them, but there are four subtypes of igneous rocks. It's based on their composition. It's based on what they're made of. And so the way that we classify these is that felsic rocks have the highest silicon and oxygen content, or what we say, it has higher silica. That's just a way of talking about the composition of a felsic rock. And an important example of a felsic rock is a granite, because we will be talking about some landforms that are made of granite. So it's nice to know that they are felsic. We have an intermediate category of igneous rocks. It just has less silica than felsic rocks. Then we have mafic rocks. They have even lower silica. Um, an example of a mafic rock is a basalt, also gabbro, but basalt is something that we should remember. And then the last subtype of igneous rocks is the ultramafic rock. It has the lowest silica, and it also has higher iron and magnesium than any of the other categories. Mafic rocks do have a fair amount of iron and magnesium, but not as much as ultramafic rocks. And this is part of what makes ultramafic rocks very dense, and they are what makes up the mantle. Ultramafic rocks, the rock that we call it that makes up the mantle is peridotite. Okay, so sorry. I have granite and basalt here uh, in bold because I wanted to make sure to emphasize that those are the two igneous rocks that you should remember. They're very important for a few different things that we'll be talking about uh, later on. So do remember granite and basalt as igneous rocks. Um, that's because here with continental crust, or no, I'll back up. In Earth's crust, the whole crust, most of it is igneous rock. And here's why part of why I said remember granite and basalt, because the continental crust, remember that was the thicker crust that makes up our land, most of it is made up of granite. There's a lot of granite in the continental crust. There's other rocks that too, but most of it is granite. And then oceanic crust, that is the seafloor. Those are the rocks that make up the seafloor. And it's much thinner than the continental crust. So even though it's thinner, it is made of basalt. And uh, basalt is mafic, more iron and magnesium than granite, and so it's denser. Granite, on the other hand, made of lighter stuff, and so it is less dense than the oceanic crust. So those are our igneous rocks. An example of igneous rocks, granites, Mount Rushmore. I've never been to Mount Rushmore, but I've heard people say that it's not as big as we make it look in pictures. And I guess maybe you can envision that since these are the trees, maybe use that for scale. I don't know. It's still pretty amazing. In any case, it was etched into granite. Batholith just means there's lots of granite exposed at the surface. So all of their faces are made of granite. That's the US presidents Washington, Jefferson, Roosevelt, and Lincoln. All right. So those are our igneous rocks, our sedimentary rock types. There are actually many different types of sedimentary rocks. But for us, the important ones for us to know are going to be sandstone, shale, and limestone. Sandstone is made of sand. Uh, we might be talking about sand that's um, the size of like sugar crystals. They're smaller than you think. Um, and those the sand from a beach or from a desert, those all compact and glue together. And sandstones are pretty resilient um, to erosion compared to shale. Shale is a very soft rock. It has very thin, fine layers. It's made of uh, mud-sized particles. So, I mean, think of a mud and turn that into a rock. Um, and that's your shale. It forms in the water. So the very fine particles settling out of that water over a long period of time, that would make shale. And again, it's soft. It's very soft compared to sandstone. And then lastly, the important rock here is limestone. It's also made in the water. And it's also considered a soft rock. But in places where there is water present, which is most places on the planet, um, water in this sense, I mean surface water like rain, rivers, I suppose. Um, Mostly rain, where it's you know. In any case, limestone will erode really easily when there's water present. It's a soft rock, and it can also dissolve in water. Sandstone, on the other hand, is the more resistant of the three, more resistant to weathering, won't break down as easily, um, because the glue that holds it together is a little bit more resistant. So in this case, sandstone, when exposed to water, um, most resistant, shale less resistant, limestone least resistant. It is the only one that dissolves in water, though, and that's because it's made of a dissolvable mineral named calcite. But those are the sorts of things that you want to remember when it comes to these sedimentary materials. Um, they're ordered here in terms of most to least resistant in the presence of water. Um, but then I'll add that in places with very little water, like deserts, limestone actually becomes very resistant because with just wind essentially out there, um, yeah, there's nothing to break it down so much. So it is really resistant in arid climates. We'll talk about that later. Here's an example of a sedimentary rock. Um, the um, these white cliffs, they are famously in Dover, England, and they are made of a sedimentary rock called chalk. And I don't mean chalkboard chalk, because most of that's made with clay. This is chalk. It's made up of little tiny algae, little tiny organisms who have little tiny skeletons, and those little tiny skeletons accumulate all the way up to make these huge cliffs. So they're pretty outstanding in pictures. I've never been there. Um, but they form underwater. It's a type of limestone, but it is, yeah, it's just an example of a cool landscape or landform from sedimentary rocks. Lastly, we have metamorphic rocks, and I'm really not going to say a whole lot about the metamorphic rocks. They get a little complicated in a way, but they are crystalline, meaning that the minerals, they are, there's no cement holding them together. They just all grew together like puzzle pieces. So metamorphic rocks are crystalline puzzle pieces, and so are igneous rocks, for that matter. And so here in the middle portion I have is that they will weather and erode very similarly to igneous rocks because of that crystalline texture that they have. Um, so that aside, metamorphic rocks do form due to increases in pressures and temperatures. As I mentioned previously, there's a threshold um, that if you go over that heat threshold, you're no longer looking at metamorphic rocks, but um, that elevated temperature is what creates the metamorphic rocks themselves. There are two categories of metamorphic rocks, whether they're foliated or non-foliated. Um, a foliation is some type of layering. That's what a foliation is. Non-foliated rocks have no foliation. They have no layers at all. And so the two pictures on the right, this top picture is layers. You see these dark layers, these lighter colored layers. See this big pink and white layer. And so that's foliated. That is a foliated rock. Below it, that is non-foliated. I see no layers. Um, the reactions that create these uh, foliated and non-foliated rocks, it does mean that we need to have an existing rock. It's called the protolith. Proto meaning like right before. So the protolith, or the parent rock, it's also called the parent, is in this case a sedimentary rock. And it's made up of a lot of quartz, like sandstones. A lot of sandstones are made up of a lot of the mineral quartz. And after the metamorphic reaction, right, that higher elevated that elevated temperature and pressure, this is our metamorphic rock. This is called a quartzite. We started with a sandstone made up of a lot of quartz, and we end up with a quartzite, all made up of quartz. So that's just an example of the metamorphic change from one rock to another. Protolith to metamorphic, or parent rock to daughter rock. Okay, these rocks also make up a lot of the deep crust with igneous rocks. Both of those make up the deep crust of Earth, whereas sedimentary rocks actually make up most of the shallow crust, right at the surface. And an example of metamorphic rocks, this one's pretty cool. The Taj Mahal in India. Was built a long time ago, hundreds of years ago, and it's made up of only marble on the outside and parts of the inside as well. Just marble. And it's a wonderful pure white marble, or it was. I think it might have colored over time. But the marble used to be pure white. Okay, so that is the geologic cycle and the rock cycle, which will lead us into the tectonic cycle next. So that is it for part 3 of chapter 11.